So this next panel is a set of three MIT professors. We also have a panel in the afternoon with PhD and postdocs. And we just want to bring as much of that cutting edge research to you guys, the attendees, the guests, the speakers, so you can really see what's happening here. The very first of the three, I don't think we have it up yet, but Professor Song Han in the CCL department he runs the Han lab. Very, very special guest to have here. I took a class with him. This is his PhD class called Tiny ML last semester, and it was one of the craziest classes I've ever taken. This last panel, I think some of the highlights of what's coming next, they spoke about small models, they spoke about edge computing, and you're going to see that. Each of these professors have a demo. But in this first one, you're going to really see what that looks like and what MIT is working on with respect to that. So I think there's still a little bit of setup. I don't know if we're ready. All right, are we ready? All right, so everyone, once again, Associate Professor of MIT, Professor Song Han, research, groundbreaking, local LLMs, edge computing. I'm going to pass over him, but please join me in giving a warm welcome to Song Han.
Thank you. All right, good morning, everyone. I'm Song. I'm very glad to introduce our research on accelerating large language model and generative AI on the edge. Recently, large language model and generative AI is getting a very big wave of new AI computing demand, where there's a lot of demand for AI computing since these models are very large and very computationally expensive to deploy on hardware devices. So software is actually quite important in the advanced technology node from 16 nanometers, 7 nanometers, all the way to 5 nanometers. You can see the proportion, the part of the software actually dominates the breakdown of the total cost for advanced technology node. The reason why NVIDIA GPU is doing so well is due to the software package, not only the hardware, but also its CUDA ecosystem, the cuDNN, the TensorRT, all the software related to map these advanced neural networks onto the hardware. So in our lab, we focus on designing new algorithms and software for efficient AI computing. Nowadays, this figure is showing the supply and demand for AI computing, where the GPU memory is growing slower, while the large language model size is growing at a much faster speed compared with the model size. And the gap is becoming larger, so it is very helpful to have model compression techniques to reduce the gap, to reduce the model size, reduce the compute, and but remain the same accuracy. This is an example of the server in our lab, 5 racks, and each one has 50 amps of electricity cable, which can power only 2 A100 server or only a single DGX H100 server. Very power hungry. We've been working on tiny machine learning to deploy these advanced AI algorithms on low-cost hardware. So tiny ML is basically to design light-weighted neural networks and deploy them on cheap edge devices, mobile devices that has low power, low compute, and low memory, low cost. There are billions of such IoT devices around the world based on microcontrollers, much cheaper, much smaller. They are everywhere in our lives, but they are very memory constrained. We designed some techniques to deal with such memory constraint so that you can shrink large model into tiny resources. For example, in this figure, in the middle figure in the middle, across the years, we've been pushing the frontier to a smaller and smaller memory size from 360 kilobyte all the way to only 32 kilobyte, while the accuracy is actually improving. So with 4 years, actually, we pushed the frontier from by an order of magnitude with even better accuracy. So MCUNet and Tiny Engine paves the way for tiny machine learning on edge devices. So here is a demo for MCUNet. which is a memory efficient patch-based inference for tiny deep learning. This is the OpenME CAM with a Cortex M7 microcontroller inside. To compare the size, we put an Apple AirPod next to it. So the size is just the size of a Apple AirPod. So we are trying to detect the person sitting far away in the lab, and we can see there is a bounding box detected for the person. Fast forward a little bit, we can also detect person in different positions, and also detect whether there is person or there is no person by attaching a tiny small microcontroller on the whiteboard. When it's no person is green, if there is a person, it becomes red. We can also put such a device in the elevator. When there is person, is red, and when the people leave the elevator, it becomes green. We can also do face and mask detection with multiple person, with mask, without mask, everything running locally on this microcontroller without sending anything to the cloud. Okay, so that's for inference. Can we also learn on the edge? Okay, so AI systems need to continuously adapt to new data collected from the sensors. Such on-device learning capability gives better privacy, lower cost, and customization capability, and lifelong learning capability. But this is very challenging because training is much more expensive than just run inference, because we need to store a lot of intermediate activations. We need to also to calculate the gradient. We also need to do the backpropagation during this process. So ideally, we want to enable edge device to learn locally and become smarter and smarter without having to send our personal sensitive data to the cloud. So everyone can have his or her own GPT model, for example, on the edge. So we have this project called on-device training under 256 kilobytes of memory, which consists of 3 techniques. First, using quantization-aware scaling to use lower bit rather than 32-bit, rather than 16-bit, we use only 8-bit for training. The challenge is that it's very difficult to converge since we have very low precision. But we use a scaling factor to deal with this issue to bridge the gap between the gradient and weight ratio that was distorted due to quantization. And secondly, we use this sparse layer and sparse tensor update. We find during human learning from adolescence time, the number of connections in the brain didn't increase, but actually decreased. So pruning process naturally happens in the human brain. And actually during fine tuning, we can actually learn just a subset of the layers and a subset of the channels. Finally, we designed this tiny training engine to realize these algorithm innovations into measured speed up. So compared with TensorFlow and PyTorch, which require hundreds of megabytes of training memory, by several techniques with tiny training engine, bring down the memory to 7 times. Quantization-aware training using lower bits reduced by another 2x. Using sparsity and pruning, we reduce it by another 8.8 times. And by operator reordering to consume those gradients immediately when they are generated and release the memory as soon as possible, we save another 2.4x memory. So all together, this actually 3 orders of magnitude reduction of the training memory, which is very game-changing, so that we can enable on-device training under only 256 kilobytes of memory. So here is a video demo running on the same OpenME CAM H7 microcontroller, an ARM core microcontroller. It has 2 buttons on the right, one green, one red, to input the labels. So red means there's a person, and you press the green button means there's no person. Initial testing is using the pre-trained ImageNet model, which can give wrong answer. Like when there is person, is not showing red. Later, we are going to manually input some labels so that we can train this model to correctly predict person versus no person, 2 classes. Okay, now let's do the on-device training. We press the red button for there's person, press the green button indicating there's no person. And we train the model to recognize between these two classes. And this microcontroller has only 256 kilobyte, half the megabyte of memory inside. So after a couple of iterations, now we can correctly recognize if there is person or no person in the image. It's quite high accuracy. And it actually generalized well for real time, real life testing. There is person versus no person after the training. This is another example showing there is no voice. So this is doing customized speech recognition.
Hi everyone. Today we are going to show a demo of device training. So the problem of current ASR models is that if some words do not appear in the training set, then the models can never recognize properly. For example, MIT is a good university. You can see it recognizes MIT to MIQ. Yeah, so similar pronunciations, but not the proper term. It's because the MIT do not appear in the training set. Therefore, we need to perform on-device trainings to enable the models to continue adapt to the new voice. So let me add some training data. I love the weather of MIT. I love the weather of MIT. And now it can use add data. Now the data is already added to the training set. So we can also perform the second one. Boston is a good place. We record Boston is a good place. We added it to the data. Now let's launch the training.
So this training is running on this JSON Nano, which is pretty cheap.
The CTC one is relatively low. So let's do the inference again. MIT is a nice school. Okay, great. You can see this time, the output properly returns the words what we want. It recognizes the term of MIT, which do not appear previously in the data set. Let's try another one. Boston is a good place. Let's again. Okay, you can see it also recognizes the term Boston properly. So we can combine it together and see, okay, MIT is located at Boston. Okay, you can see now it recognizes the two terms properly.
Okay, so this is showing that it's possible to run actually multi-model training locally on the device. It is running on the JSON Orin, and we can reduce the latency from 20 by actually 1 order of magnitude, and reduce the memory also from by an order of magnitude with the same word error rate. And last year, our project was highlighted by MIT News to not only support this visual and audio on-device training, but also large language model pre-training locally on a mobile GPU, the JSON Orin, NVIDIA JSON Orin. This is fine-tuning Llama 2, which has 7 billion parameters. But thanks to this sparse update, we can smartly find a subset of the weights that are contributing when we are doing the fine-tuning. And it's very helpful to do the fine-tuning. For example, before fine-tuning, we are given a task, I love the micro conference. Please reverse the words in the sentence. Without fine-tuning, Meta's Llama 2 7B is going to say, I hate the conference micro. Micro is a very prestigious conference in computer architecture. After the tuning, it's going to say the reversed result is conference micro, the love I is correct. And we reduce the latency from 7.7 seconds to less than a second. So everybody can have his or her own large language model catered for your need and put it in your pocket. So ChatGPT is very expensive. Now let's switch gear from this tiny model to this large model and see how can we reduce the cost of these large models. So we propose its on-device LLM by quantization. So using smooth quant and AWQ activation-aware weight-only quantization by reducing the precision, reducing the bits to only 4 bits. Previously, we need 16 bits to store the weight. So a 7 billion parameter model takes 14 gigabytes. With only 4 bits, we need only 3.5 gigabytes to store that model. But unfortunately, these outlier channels make it difficult to quantize, and accuracy is degrading very severely. So by smoothing, we can make the activations much smoother and make it easier to quantize by shifting the quantization difficulty between the weights and activations, so that we can run the large language model locally on your laptop without connecting to the internet. For example, here we are asking it to write a program to sort an array in C, and then it's going to tell you the answer. Actually, I have a live demo here to run this model. I can turn off the Wi-Fi and then let it to run the tiny chat locally on my MacBook. It's using the AWQ 4-bit quantization. I can let it tell me 3 attractions in Boston, since many of you traveled far away. And then let's see what does it recommend. So it's giving a pretty fast answer, tell us several attractions, including the Freedom Trail, the Family Park, and Museum of Fine Arts. And the Wi-Fi is off, everything is running locally on my laptop. So we open source this project so everyone can now download this tiny chat by scanning this QR code. It's MIT license, commercially permissive. Feel free to download it. It supports many models, including the Llama 27B, 13B, and Code Llama, and also visual language model as well. We also collaborated with Quincy and many designers to build a tiny chat computer so that you can run this tiny chat locally on an edge device, purely powered by local compute without connecting to the internet. It's resource constrained, low power, preserve the privacy, and it's powered by a small JSON Ori Nano in the back. It's very cheap. And this project also has been adopted by NVIDIA. Now it becomes the chat with RTX. It's also free to download. You can use the capability to locally chat with your RTX laptop. And it's been widely adopted by industry. It's an open source project. Everybody is welcome to contribute. By NVIDIA TensorRT LLM, by Intel Q8 Chat, and also Berkeley VLLM, Berkeley Fast Chat, and IBM Granite, and a few startups. So beyond the language, recently, visual model is also computationally intensive. So we want to also speed up the visual transformers, especially for these high-resolution visual transformers. As the resolution gets larger, like low-rise, like more than 3K. 4K or 3K, right? That require a lot of tokens, which is quadratic to the resolution. And the attention mechanism used in visual transformers grow quadratically with the number of tokens. So everything put together becomes very expensive to run. And efficient VIT introduces this lightweighted multi-scale linear attention to replace the softmax attention, and can drastically improve the speed. For example, previously, NVIDIA SegFormer ran only about 1.6 FPS with the Orin platform, which is autonomous driving AI chip. With efficient VIT, it runs more than 20 frames per second on the same driving AGX Orin platform. And for the segment anything model, it runs more than 48 times faster and has been adopted by many products inside NVIDIA. So talking about visual and language, can we combine them together to build a visual language model that can understand both image and also language in the same model and be able to deploy them on the hardware, on the edge device? Okay, so we propose this VLA, the visual language model, VLA, on pre-training of visual language models. So the goal is to understand both visual and language without hurting without destroying the large language model. And it's even more computationally intensive to deploy on the edge, since it contains both visual model and also the language model. So the VLA proposed a very efficient training and deployment recipe so that we can actually deploy them on a JSON Ori. For example, here we ask, what is unusual about this scene? Are there any safety concerns? Can use it for IoT applications. And it can answer in the image, there's a person hanging on a rope of a wind turbine blade. There's a risk of falling from there is significantly large. And also in some smart factory applications, we can also query what's happening in the factory, what is happening in the workshop, like how many cars are jacked up, what is the color of the person, what is the brand of the car. Previously, we have to train many separate models to run different tasks. Now, just one single foundational model, a single visual language model that you can query it with many different tasks. And even about these corner cases, which is very difficult to handle for L3, L4 autonomous driving, but now we can use the language model to support this visual recognition to handle this corner case where there's a lot of deer crossing the street. And most amazingly, this can be deployed on the edge, so many EV companies are very interested in this work. We also made this public available, so feel free to go to Vila-demo to check out the demo. For example, to echo with the next speaker, we prepared a demo related to, since I'm not connected to internet, this one requires the internet to run. The visual language model demo is running on a 6,000 server we put up in our lab. For example, we can put up the multi-image reasoning at the Earth in 1984 versus 2012 in the Arctic. And we ask, what is the implication of the temperature based on this image? It can tell us it's showing the comparison of the Arctic ice cap in 1984 and 2012 suggests the temperature, the reason has increased, which have a negative impact on the ecosystem and wildlife. We can also ask it about some medical applications, like will the person being rescued feel pain? They're actually learning on a dummy person. So let's see how does it answer. It can tell me, oh no, the person being rescued is a mannequin, is a dummy person, because this is a group of students. Figure for training purpose is not a real person, so it cannot feel pain. So actually it can run a lot of good reasoning. It can even run such kind of in-context learning. In-context learning is a special capability emerging when the model gets larger. We are not telling it a task, but the task is embedded in the question itself. For example, the first image is famous for its search engine. Second image is famous for Mac and iPhone. And third image, we are not telling it what is the task, but you want to infer from what the task is. And it can give us the answer it's famous for is GPU cards and chips. All right, so let's go back to our presentation. So beyond this discriminative model, we also want to accelerate these generative models. For example, the image generation, video generation, like recent Sora is very hot, and we need to accelerate such high-resolution diffusion model inference by leveraging the GPU parallelism. So previously, we were dealing with just a 1K or 720, those low resolution, but dealing with high resolution is very crucial. We work on this distributed parallel inference. If you have 4 GPUs, can you become 4 times faster? So naively doing this, so this is giving the prompt ethereal fantasy concept of an art of elf, magnificent, etc. So this is just using 1 GPU, require 12 seconds to generate 1 image. 12 seconds is too long to generate. But naively using 4 GPUs, it indeed gets faster, like 3.9 times faster, but actually it generated 4 such figures. That's not what we want. And we find the reason is that such naive parallelization needs to lead to strong artifacts due to the lack of patch interaction, no communication, no attention between the patches. That leads to us generating actually 4 figures. So our solution is called distribution, distributed diffusion model. Okay? Communicate the patches. Well, we can hide the communication latency by using the fact that adjacent diffusion steps are similar. So we can just use the previous step to communicate. We are communicating actually the old step so that we can overlap communication with computation. So that with 4 GPUs, we can get about 3 times faster. Well, there's no artifact compared with naive parallelization. So there is still about another 30% of room of improvement for the 4x theoretical speedup. And finally, we have the streaming LLM project. You want to interact, since ChatGPT is just so useful, you want to continuously interacting with it. However, with fixed GPU memory, you soon will break the performance because the model will run out of memory as the KV cache gets longer. The KV cache stores all your previous history, stores all your previous chat history. So how do we enable this long chat? For example, when you are driving from Boston to New York, we want to continuously use these chat capability for 5 hours. So this is using streaming LLM. We find by preserving some key tokens, we call it attention sink tokens, by preserving them, always pinning them in the KV cache, just like pinning the page in the page table in the operating system, just pin those important KV pages, we can stabilize the inference dynamic. So this is our MLC chat implemented the streaming LLM on the iPhone. You can have this very long conversation on and so on. So having such long conversation does not lead to you remember all the old stuff. Recently, Google's Gemini has like 1 million history token. You can remember a long context to even understand the whole book of a novel, right? But fine-tuning the model for long context is very expensive unless you have thousands of GPUs. What if you have only one machine, you have only 8 GPUs? So we propose this sparse and shifted attention. Okay, we are again using sparsity rather than using the full fine-tuning for the entire matrix attention. We only allow this sparse attention, block-wise sparse attention. So the complexity is no longer O(n) squared, but it's O(n) times m. M is the width of each block. And we shifted to allow information to flow between different blocks. And altogether, we can fully match the accuracy of full fine-tuning while reducing the training hour by a large margin. So only using one GPU machine, we can fine-tune, extend and fine-tune the context length of Llama 2 from 4K to 100K tokens. We've been also working on generative model acceleration for real-time photo editing. It used to be pretty slow. For example, make the lady smile. It takes about 3 seconds to run it locally on laptop. And designers may want to have this interactive interaction with the generative model. Okay, so we can use this technique called any cost GAN. We train a super network that can have many sub-networks that can independently operate. So at runtime, in the editing stage, we can pick a low-cost sub-network to run for fast prototyping. Okay, we can make the lady smile by dragging the sliding bar to the right, or we can make her look younger by dragging the second bar, and it's taking only 0.4 seconds, instant result. And after the editing, we feel comfortable, then we can click the finalize button, which run the full network, okay, the full network, which share the weight with the small network. And as a result, we can actually drastically reduce the computing required for running this model from 100% to 59%, 39%, all the way to only 19%, but still give very high fidelity generated figures. Okay, finally, in the autonomous driving area, computation is also a big bottleneck. We don't want to have a full trunk of GPU computers in the backpack, in the trunk of your car. So we propose this BV fusion for multitask, multi-sensor fusion from a single sensor to multiple sensor. And we here deal with both dense camera data and also the sparse LiDAR data and merge them together for multi-sensor fusion for 3D detection, detecting the bounding boxes of each driving car, and also do the road segmentation without a map for mapless driving. And this can run locally on a Jetson Orin, became the reference design for NVIDIA when they are setting their Orin chip. Finally, to democratize this line of research, I developed this efficient ML.ai course expanding between inference training and also application-specific optimizations. Everything is available online. Welcome to check out the YouTube to watch the lecture. It contains 5 labs. After containing the 5 labs, you will be able to deploy a Llama tool, deploying a large language model locally on your laptop. It'll be pretty fun. And finally, many thanks to my collaborators and sponsors, and all the slides and demos I described today are available on our website and also YouTube channel. Feel free to check it out. Thank you.
So it's my pleasure to announce our next speaker, Dr. Martin Reinhard. Dr. Reinhard is a professor in the Department of Electrical Engineering and Computer Science here at MIT, and a member of the Computer Science and Artificial Intelligence Lab, more commonly known as CSAIL. I'll turn it over to Dr. Reinhard, where he can introduce himself and the amazing work he's doing. Thank you.
All right, thank you very much for that introduction. It's great to see everybody here today. Every project needs a problem. Here's our problem. Our problem that we're attacking here is that people die of cancer because they're diagnosed too late. First thing I'd like to do is give you an idea of the scale of this problem. What you should take away from this is a lot of people get diagnosed from cancer, a lot of people die of cancer, and it costs a lot of money to take care of them while they're dying or hopefully surviving. If it turns out that you're diagnosed with cancer, you would much rather get diagnosed with an early stage cancer rather than late stage cancer. You look at the 5-year survival rates, they're much higher for stage 1 cancer than for stage 4. So one of the goals of this project, in fact, the primary goal of this project, is to convert people from being diagnosed with stage 4 cancer or late stage cancer to being diagnosed with early stage cancer. It turns out that also it's cheaper to care for people if they're diagnosed early than late. So there's a financial incentive as well to be sure that we get this early stage versus late stage diagnosis. All right, so now the question is, what are we going to do about this problem? Here's what we're going to do. We've established a collaboration with this company called TriNetX. This company, their business is they go out, they acquire people's healthcare records from healthcare organizations, they integrate them into a large network, and then make this information available to various organizations, and including our research group. What we do is we take this large trove of healthcare information and build a model. These are machine learning models, and the goal of the model is to identify high-risk patients. For example, as you'll see, we would like to identify patients 6 months to a year when they would otherwise be diagnosed with later stage cancer. Now, the great thing about this is they're continually getting updates from the medical record. So if you go in and you have a doctor's appointment, you get a blood test, you get a diagnosis, the doctor prescribes medications for you. All of that goes into the system, and it's continuously fed out. We can access this in basically real time as soon as it goes in. So now what we can do is we can continuously monitor the patient population, and when someone goes high risk, what we can do is we can identify that patient. We can have now a reverse path back to the provider to inform the provider, hey, here's a patient that is at high risk, or according to our models at high risk. You may want to go off and do additional screening. So this automates a lot of the process that the doctor would otherwise have to do. They're sitting there looking at the patient record. Many cancers have obscure or not so clear indications that this patient may be at high risk. So we're trying to automate that and say what the next step should be. So now, once we have identified this patient at high risk for cancer, or whatever cancer you have, our anticipated use case is a tiered use case where we're working with data that's collected as a normal part of the medical process. Nothing has to change. Nobody has to be aware that they're even being screened, okay? So now, once we identify high-risk patients, we then recommend going off to additional screening. There's biomarker screening where you take a blood test or a saliva test, things like this. And now the patient is becoming aware that, hey, there's additional screening going on. There are very many companies out there. Cancer research is a very active area of research. There are very many companies that are developing biomarkers, and the problem they have is somehow you have to find the right patients to apply these biomarkers to. And one of the use cases for this is we identify the people where it's profitable or worthwhile to apply the biomarkers to these patients, as opposed to just doing it across the entire population, which is now not economically or socially feasible. So you can also do imaging as well. Again, more expensive, but worth it depending on your trade-off for the number of people you get for the investment you make. All right, so there's very many cancers, and it turns out that one of the things I've learned as part of my participation in this project is that all cancers are different. So our first cancer model is for pancreatic cancer. Let's size this problem, okay? We got 66,000 new pancreatic cancer patients per year. This is per the American Cancer Society. 1 in 58 lifetime risk for men, 1 in 60 lifetime risk for women. For women, 3% of all cancer cases, but 7% of all cancer deaths is because it's a fairly lethal cancer. It's a very challenging cancer to diagnose early because many of the indications are, obscure. You don't know exactly what's going on. Something's wrong with the person, but you can't tell exactly what it is. So most patients are diagnosed at stage 4, very poor prognosis, 13% 5-year relative survival rate. There is a current standard of care for screening people, and that is if you have a family history of pancreatic cancer or you have a genetic syndrome like Lynch syndrome or maybe BRCA, then this is like 2% of the population. They'll put you in for an annual MRI or endoscopic ultrasound screening. And what this does is it lets 10% of the cases be found in stage 1 as opposed to stage 4 when basically there's very little hope for treating the patient successfully. So here's what our model looked like. We went off and built 2 models. The first is a neural network model. The second is a logistic regression model. You can see that these are traditional machine learning models, but still we're getting very good performance if you look at the AUC curve. And in fact, our feeling from working with this data isn't that the limiting factor is the sophistication of the model, but rather that the limiting factor is the amount of information present in healthcare records, which these models are effective at extracting and making good predictions. Now we can operate this, okay, so what are the features we're looking at? Medication types. If you're prescribed a medication that's in your medical record, that's one of the features we take a look at. Lab values. You go in, they do things, they draw blood, they measure various things about your blood test. Those are more values we take a look at. And finally, diagnostic codes. So we can operate this model anywhere along this AUC curve. And the trade-off is that you get more people, but you also have higher false positives. So here's one potential operating point, where we identify 5% of the population as high risk. Of those 5% identified as high risk, a little bit less than 1% is going to be diagnosed with cancer in the next year based on our retrospective analysis of the data that we've been working with. And we ideally hope to get 30% of all pancreatic cancer patients in this high-risk group, so we get them early. So here's a deployment scenario. Every month or every week or whatever it is, we compute a risk score for all patients across the entire platform. Okay? We notify the provider for high-risk patients, and we are going to recommend a tiered screen. It turns out that there's CA19-9. This is a blood test for pancreatic cancer. Okay, if it turns out that you're positive on the CA19-9, we'll send you off to MRI in the U.S. The reason we're doing this is because if you send everybody off who's high risk, you're sending 5% of the population off to do an MRI or an endoscopic ultrasound. This is not feasible in the current situation right now. So at the end of the day, you can look at the numbers we go down here. The key numbers are that CA19-9 if you actually do have pancreatic cancer, 65% of the time it'll say so, the rest it won't. That costs $100 per patient, so it's relatively cheap. If you're positive on that, we then send you off to MRI or endoscopic ultrasound. That's $840 per patient. And with this, we expect to get 16,000 patients diagnosed at stage 1 instead of stage 4 per year, which is, we think is a pretty good result. Key question is how many people are we going to screen like this? Well, the first thing is the vast majority of pancreatic cancer patients happen in people over 50. So we're not even going to send the majority of the population that's under 50 off to look at high risk if that happens, okay? So that's 123 million people. We're going to send 6 million off to do the CA19-99 and about 307,000 sent to the MRI. Now, the key caveat here is this assumes that there's sufficient medical history. Our model needs sufficient medical history to compute a risk score for you. And right now, because of the way the electronic health records run in this country, we don't have complete electronic health information or sufficient electronic health information for everybody. Over time, as the electronic health records become better and the systems become more organized and integrated, we expect the proportion of the population to rise. Okay, what's our current status? About a year ago, we went into the Trinetics network and we computed risk scores for 6 million patients. We don't know who these patients are. We can potentially re-identify them, but even if we have a very high risk score for a patient, it's a very big step to go off and start running screens on this patient. So we're not doing this. This is a prospective study. Okay, we're going to get our 1-year results in April, and we'll see how well our model performs prospectively as opposed to retrospectively. We've also been using our model in a pilot study at Beth Israel to recruit high-risk patients for their pancreatic cancer studies. Turns out that because we have an exceptional researcher, as you'll see, Kai Jia, working on this, we're in a position right now where we can type in a few numbers, hit return, and we get initial models for basically whatever cancer we want. We've got a bunch of initial models for all these other cancers, and the performance varies depending on the cancer. And what we anticipate is going to happen is we'll just go through and knock them off one by one, see what the model looks like, see what the best tiered approach is, and we'll go through and knock off these cancers one by one. Okay, what do we want to do? At this point, it's pretty clear that we've been running this project as an academic project for like the last several years. If we really want to take this project and realize its potential, it's time to transition out of academia and have a professional organization who's doing this project. So we got to fill out, so there's a bunch of technical things we're going to do, fill out the portfolio of the cancer and other models. There's no reason we can't predict other syndromes as well, if it's useful to detect them early. Identify the most promising models for deployment. Now we got to do the whole business model thing, execute the project, all this kind of stuff, okay? And that's something that we're just now starting to think about, how we best take the potential that we think we have here and bring this out into the real world. So here's who we are. This is a great collaboration. We've got Limor Applebaum, who's here today. She's a radiation oncologist, and this collaboration started because she reached out to me and we decided to fire on this. Kai Jia, is an exceptional applied ML engineer. He developed the system and the initial models. I'm the professor. I kind of sit around and organize everything and give talks like this. And so here's the bottom line. Use electronic health records to identify individuals who are at high risk for cancer. We're going to use a tiered approach where the key advantage is we can do this very cheaply in the initial stages. We don't have to have any changes in the existing medical procedures to identify high-risk patients. We work with data that's already available. The patients don't even know that we're ranking them and computing risk scores for them. And the ultimate goal here is to convert late-stage diagnosis to early-stage diagnosis. And as the numbers you saw in the early part of the talk will indicate, what we will get if this is accomplished is higher survival rates for what right now are very deadly cancers, and reduce cost of treating these patients. Okay, so here we go.
Great talk, Dr. Reiner. I was curious if you could talk a little bit about the model itself. These EHR records are typically temporal data, and I know you mentioned NN.
That's a great question, because as I think everybody in the audience knows, when you start dealing with medical data, there's huge problems because of the heterogeneity of the data, how it's distributed, all the different ways it's represented. One of the key advantages we're starting with here is because of our collaboration with this Trinetics company, they've done most of the data wrangling for us. So we're already working with data that has been, in some sense, put into a uniform format that we can work with. Mm-hmm. Then we have to go off, and as you point out, temporal data is very hard for these models to work with. So we've had to go in and engineer features that are appropriate that allow us to do this. So we're still, this is very much sort of traditional machine learning and AI. We're comfortable doing that because of the kind of data we're working with, where we think we're going to get most, if not all, of the information in that data using these techniques. But you're right, that what you haven't seen in this talk is the sophistication of working with this data and the amount of technical problems that we had to solve, which we have now solved thanks in part, actually thanks almost entirely, to the amazing technical ability of Kai Jia, who's working on this project.
All right, thank you.
Yeah.
I have a question about the EHR data, because like my company, it's basically doing the same thing that we build out prediction model on the microbiome and the clinical health record. And I'm dealing with the EHR a lot, and I know, like, I'm so impressive, like, how messy and disorganized they are. Yeah, so we spend like tons of time to store the data. We're also trying to leverage the large language model to read, to extract information from EHR.
Yep.
So I'm wondering how you solve the issues of, messy EHI data. Like, did you leverage any generative AI into the step? What's your, process?
So our group did not leverage generative AI to do like NLP and things like that, reading doctors' records. In part because we're standing on top of an existing organization that's very well funded to deal with all of the messiness that you're talking about. So that's part of the reason we are able to do this kind of project and get these kind of results at this scale with this kind of data. It's that collaboration. So having said that, that company's expertise is not in this area, right? Their expertise is interacting with HCOs and getting the data and putting it in a format where now organizations such as ours can use it. So, but you're absolutely right. And I think this has been one of the barriers to exploiting the, in my view, incredible potential that's available using all this EHR data is how it's siloed in different organizations. Privacy concerns make it different. You've got massive data wrangling problems. And we're in a position, I think a very fortunate position, where we've been able to deal with most of those problems effectively. And what you're starting to see here is the true potential that you can get once you have that data available in a more malleable, more accessible form. So, yeah, I hope that answers your question.
Thank you so much, Dr. Reinert. Our next speaker is Dr. Noman Bashir. Dr. Bashir is the Computing and Climate Impact Fellow at MIT Climate and Sustainability Consortium. Please join me in welcoming Dr. Bashir.
Hi everyone, as Priya mentioned, I'm Noman. I am Computing and Climate Impact Fellow at MCSC. I am also affiliated with Christina Delometro's group, SAIL at MIT CSAIL. And before I go into the topic of my talk, I will provide a brief overview of my research background to give you an idea how I reached this topic of climate and sustainability implications. So, my research has been at the intersection of energy, computing, and society. So I have been on both sides of the aisles in terms of using data-driven ML methods to decarbonize other sectors. So in that space, I have worked on enhancing energy systems, performance, electric grids, so electrification, and also like enabling society to transition to a more kind of climate-friendly energy. And also, like I have worked on the pure computing side, where the goal was to either increase the resource utilization of data centers and other like edge computing paradigms. And finally, my recent work has been kind of a combination of all of these efforts, where it looks at the sustainability of computing. How, like, what does it mean for computing or clouds to be sustainable? What are the options for us? How can we use computing's workloads flexibility to decarbonize computing? So given that, and this work has been across, like, in collaboration with a lot of like groups at Caltech, UMass Amherst, and Google, IBM, and other places. With that, I will start talking about my current work. So we all know that we have heard this, that artificial intelligence is increasing computing demand, and this is becoming more of a problem. And if you look at this graph on the left, we have power demand in megawatts for data centers that are being constructed every year. So if you see from 2019, there was a relatively small growth, but then in 2022, after ChatGPT, like it kind of went into a exponential phase, exponential growth phase. And this is just, this is the actual, not the estimated or the future data centers that will be built. So we see that the demand is increasing massively. And this is not going to stop, because this is just like on the right side, I have just two examples of what the future capacity is going to look like. For example, just for co-location capacity, I'm not talking about the companies. These are the co-location facilities, where 12,000 megawatt of data center capacity is already scheduled to be built before 2030. And this is basically more than the energy or the electricity capacity for 80% of the countries worldwide. And big companies alone are building massive data centers. For example, Google in just 2 locations, Norway and Sweden, in 2 data centers is building 2,000 megawatt data centers over the next decade. And then what does it mean for these data centers? So what happened, like if you look at the bottom numbers, if we go from 2005 to 10 and 2018, the energy consumption of computing remained relatively like constant. Like if 2010 to 2018, it increased only by 6%. And the reason was there was massive efficiency gains because of people moved from on-demand, on-premise data centers to hyper-scale cloud data centers, which were way more efficient. However, now as the efficiency gains are slightly slowing down, then the increase in demand is resulting in increase in energy consumption. So in 2022, within just like 4 years, it more than doubled to 460 terawatt hour. And in the next like 4-year phase, it is going to double again. And only like, I don't know who can predict what the future is going to look like with all this demand. So what is the problem with this like increasing demand? I think the one of major problem is incomplete consideration of values. Currently with generative AI or AI in general, we are just looking at the bright side of things, like what it can do for us. How can it improve luxury? How can it improve necessities? How can it improve like efficiency in all sectors of life? However, there is also a not so bright side that is often ignored, and it is not just about the energy consumption, even though like in the last slide I focused on the demand and as well as the energy consumption, but it has multifaceted impacts. There is e-waste problem, resources are being depleted, and then water scarcity is going is now being talked about because data centers use massive amount of water. And then GHG emissions and energy shortage is kind of like the common word now, but there are also impact on people and impact on biodiversity. So there was an interesting conversation last night where I was suggested that markets will handle kind of like this problem, which I understand the sentiment, but the problem is that for a lot of these issues, people being impacted don't have a voice in the market. People who are in other parts of the world where climate impacts are severe, they don't have a voice in US economic market and they won't be able to influence anything. So this incomplete consideration of value is driving this unfettered growth in generative AI. So what is basically like, what are the key drivers behind it? So in our research, we basically like outlined 4 major drivers. First one is, just like I said, perceived benefits. Like there is this assumption that AI is going to transform every single sector in every imaginable possible way. So that is driving the growth. Then the efficiency improvement has enabled training and inference of large-scale models, allowing it for more people to use. So that has helped it. Then consolidation of AI capabilities within big tech has definitely accelerated the growth, because now you have 10,000 AI engineers within a single space that can collaborate and brainstorm and accelerate the AI research. They also have massive computing facilities where they could train billions of parameter models, which was not possible before. And then there is definitely lack of regulatory oversight. And I'm not saying all of these things are bad. I'm just saying that these things have contributed to this unfettered growth in demand. So what does this mean? Does this mean that we should stop working on generative AI or stop the growth? The answer is no. Instead, in our group, recently MIT president last year gave a call for MIT perspective on generative AI, and people submitted research proposal to write papers on it, and one of like ours was one of those. And in our paper, we looked at the climate and sustainability implications of generative AI, and it had a broad participation from different research groups at MIT, including all the authors that I have listed here. So what do we propose basically? One context before I come to our proposal is that recently there has been two major legislation passed within the last week or so. So in fact, yeah, SEC ruled on climate disclosures for corporates and organizations, that they need to declare their scope 1 and scope 2 emissions, which are because of their direct use of energy in their operation or the energy usage from electricity they purchase to run their thing. And secondly, last month, there was a bill from Massachusetts Senator Ed Markey on which basically asks people to investigate and quantify and measure the environmental impact of AI. So our research is, we will work with their office to enable implementation of such regulation where you could investigate and measure the environmental impacts of AI. So how do we propose to do that? So in industrial ecology, there is a well-defined method of investigating the impact in terms of life cycle assessment, where you define a scope, like which is very, very like well-defined application. You define your boundaries, you define your baselines and scenarios. It could be, for example, standard Google search versus ChatGPT-based search. And then you have certain metrics and data to quantify the impacts. And this, I'm not going too much into the details of this like example, but the idea is to quantify basically the compute-related impacts, the benefits that happen at the immediate application scale. Let's say you are doing search, you find your results much faster. Or you are doing coding, you don't have to spend as much time basically going through the writing documentation and whatnot. So, and then finally, there are system level impacts of people using generative AI tools. So our goal is to provide this evaluative framework, which enables people to reason about the costs and benefits. Because in like, there are recent studies, for example, with Copilot, GitHub Copilot, it's really good at writing documentations or single functions, but if you ask it to refactor code or write complex programs, it ends up increasing your total time and does not help in productivity. So our idea is to basically ask people to be in this evaluative kind of mindset where they quantify the benefits and cost and try to maximize the value of their generative AI tools and apply it first to those applications where you get the most benefit. And this is not a straightforward process because as you can imagine, quantifying the costs as well as the benefits is not a straightforward problem, and we need a lot of like support from different stakeholders, from policymakers and legal experts to enforce regulations around asking people to disclose their energy usage information, carbon usage information, AI practitioners and engineers to basically help us with quantifying the costs or reducing the cost to tip the scale in favor of generative AI, and then supply chain and energy and supply chain experts to quantify the cost on the embodied carbon or embodied impact side of things, and then social scientists to help with like benefits that are happening within the society because of these tools, and end users definitely where they feel this thing to be most useful. So with that, I will conclude my talk, and I will ask people in the audience, like if they find this interesting and they think they can contribute to our research in developing this framework, please reach out to us, and we would be happy to like work with you to get your perspective into this